An array-based linked list, often referred to as a static linked list, is an alternative implementation of a linked list in which the nodes are stored inside an array, rather than being created dynamically in memory using pointers. Unlike a traditional linked list that uses dynamically allocated nodes with next pointers, an array-based linked list stores all elements in a fixed-size array, with each array index acting as a node that contains both data and a link field indicating the index of the next node in the structure. This approach combines the characteristics of arrays and linked lists, providing the benefits of linked list-style insertions and deletions while operating inside a fixed, predetermined block of memory, instead of using actual memory addresses as pointers. Static linked lists use integer indices to navigate between nodes. This structure is particularly useful in memory-constrained systems, embedded environments, or educational contexts where pointer manipulation is either restricted or undesirable. The fundamental idea behind an array-based linked list is that each element of the array represents a node with two components: a data field that stores the actual information and a next field that stores the index of the next node in the logical sequence. A special index, often called head, marks the beginning of the list, while a separate pointer known as a val or free list pointer maintains the index of the first free or unused element in the array. When a new node needs to be inserted, the first available index is taken from the free list, its data field is filled, and its next field is connected to the appropriate node in the sequence. When a node is deleted, its index is returned to the free list so that it can be reused in future insertions. This recycling of indices ensures efficient usage of the fixed memory block. The implementation thus creates a chain-like structure within the array by linking indices instead of memory addresses. Creating an array-based linked list begins with initializing an array of fixed size, such as max equals 100. Each element in the array contains a structure that includes the data and a next index. The next fields of all nodes are initially set in such a way that they form a chain of free nodes. For example, the next of index 0 points to index 1, index 1 points to index 2, and so on, with the last index pointing to -1 to mark the end of the free list. The aval pointer is then set to 0 because the first free node is at index 0. Before any insertion occurs, the list is logically empty, meaning that the head pointer is set to -1. This setup allows the program to know which memory spots are free and which form part of the linked list. The careful arrangement of free nodes during initialization ensures efficient memory allocation. During operational phases, insertion in an array-based linked list follows a structured process. When the user wants to insert an element, the program first checks whether the aval pointer is -1, which would mean that no more space is available in the array. If space exists, the node at the aval index is taken, its data value is updated, and the aval pointer is moved to the next free index. If insertion is at the beginning of the list, the new node's next field is set to the current head, and the head pointer is updated to this new index. If the insertion is at the end or at a specific position, the array is traversed using next indices until the correct location is found, after which the next fields of the surrounding nodes are updated. This index-based linking preserves the dynamic flexibility of traditional linked lists while avoiding pointer-related complexities. The primary advantage is that insertions do not require shifting of elements, which is a major drawback of simple arrays in standard implementations. Searching within an array-based linked list is similar to searching in a traditional linked list, except that indices are used instead of pointers. Starting from the head index, each node's data field is checked sequentially, The search continues by following the next index stored in the node until the target value is found, or until -1 is encountered, indicating the end of the logical list. Because the structure is implemented inside an array, searching remains a linear time operation with O(n) complexity. One notable advantage of an array-based implementation is improved memory locality compared to dynamically allocated linked lists. Since the nodes exist within a contiguous block of memory, accessing sequential nodes can be faster due to caching benefits on modern architectures. However, this is balanced by the lack of true dynamic memory expansion, making it less suitable for situations where unpredictable memory growth is expected. Deletion in an array-based linked list involves locating the node to be deleted, adjusting the next fields of adjacent nodes, and returning the deleted node's index to the free list. If the node to be deleted is the head node, the head is simply updated to the next node in the list for deletion at other positions. Traversal is required to find the node preceding the one to be deleted. Once located, the preceding node's next index is updated to bypass the deleted node. The deleted node is then added back to the free list by linking it to the previous avail index and updating avail to this node. This mechanism ensures efficient reuse of array space and prevents memory wastage. The major constraint is that the array size is fixed, limiting the number of elements the list can hold. But memory fragmentation is avoided entirely because static allocation ensures contiguous storage. Displaying or traversing an array-based linked list involves starting from the head and following the sequence of indices until -1 is reached. Each node's data value is printed or processed, creating a logical view of the list. This operation is simple because, despite using an array, the list behaves like a normal linked list in terms of sequential logical access. The advantage is that display operations never access unused array positions because logical traversal follows the next indices rather than the physical array order. Thus, the representation remains consistent even when nodes are stored non-contiguously in the array. In conclusion, the array-based linked list is an efficient hybrid structure that blends the advantages of arrays and linked lists. It provides predictable memory allocation, avoids pointer manipulation, allows fast insertion and deletion, and supports dynamic logical structure formation within a fixed memory block. Although its fixed size limits scalability, its clarity, safety, and deterministic memory usage make it ideal for environments where dynamic memory allocation is restricted or unavailable. Understanding this structure helps learners master indexing logic, memory management principles, and linked list-like operations without relying on pointers, making it an essential topic in data structure education.